So let's look at some of the characteristics of generators when they are operated in parallel. So before we go into that, our first instant will be operating singly. So generally, and I will take you back to what we talked about the last lecture we met, generally you would note that in terms of a voltage that is supplied by a generator, as electrical loads vary, the voltage is maintained by changing excitation. And we said that out of all the things that we will learn within this unit, the most important is that one. The voltage is related to the field current or the excitation. All right? That is key number one. Key number two is that in terms of production of power, all right, the power that is generated is dependent on the prime mover. All right? So the prime mover is the one that controls power and at the same time frequency. Right? Power and frequency are very closely tied to each other, and they are mainly manipulated by the action of the prime mover. If you need to supply a greater load, you must put in more from the prime mover. This makes sense in terms of physics, in that if you are, lifting some load and the load is 100 newtons or whatever it is, you must be able to put in to the motor as much power as is required to carry out that work. The same thing applies to generators. If your load requires 50 kilowatts, you must have, the prime mover must rotate the generator in such a way that it can produce 50 kilowatts, right? So the energy put in must match the energy being put out. And at the same time, the prime mover is the one that determines the frequency by determining the speed. So one additional thing that we would want to include here is that while the prime mover affects active power and frequency, the excitation of the machine or excitation of the generator affects the voltage as well as reactive power, or Q, right? And IF, or excitation, in practical generators is called the voltage regulator system, right? And on this side, active power or the prime mover is regulated by the governor. So these two are the main means by which we alter the operation of the generator in terms of the loads that we need to supply. So when a generator is operating, those are the two key elements that you will need to take care of, or you will need to remember. Always remember, the voltage regulator varies voltage and reactive power. The governor varies active power and frequency. So having known that and having said that, let's now get into how generators operate as the loads are varied, all right? Because this is all about the characteristics of generators when they are working under load. So now let's first of all look at the active power being regulated by the governor. So the action of the governor is such that when you have a speed at no load compared to a speed at full load, you would tend to have a droop or a drop, which is called speed droop. All right. Governors are set up such that they give a linear relationship between the speed and the power that is being supplied. And that relationship is usually known as speed droop, right? And you will now see that the relationships between these ones are both linear. On the other hand, let's move this to this side. And when you look at the relationship for a voltage regulator, the same thing applies. So voltage regulators ensure that there is a linear relationship, and this is controlled by varying the field current. Okay, so in both cases, so in the case of power, you will have power is equal to SP into no load frequency minus frequency of whatever system there is, whereby the power is, this is active power or generator output. This is now a slope of a characteristic we will see shortly. This is your no load frequency of the generator at that particular set of generator settings. And you have system frequency of the system that you are supplying. Okay, so now let's look at what those characteristics look like. So you can see side by side, we have the two relationships that we were talking about. Here on this side, we have your real, let's call it active power. And on this side, you have reactive power. And those are the relationships between the two. And you can see that you have a slope SP that determines the characteristics of the reaction of the generator to any change in the load. The droop of speed. The generator at a certain power, when it is supplying a certain power FL, let's say the full load power, it will be at a frequency that is given by that. As you go decreasing the amount of power that the generator is supplying, the frequency of course will increase, yeah, naturally, because of the characteristics of the governor. So the governor keeps that relationship in a linear form. So what you will then see is that if you would require certain power to be supplied at a certain frequency, you need to have a different value, not a different value of SP, but a different value of F at no load. Okay, so what do we mean by this? We mean that in case you want a certain power P, let's say there, P1, but you want to supply it at this frequency, yeah, under the governor settings that you have. So this slope is given by the governor settings. We call them set points. Under the set points that result in this slope, your full load power will be at a frequency of here, FFL. But if you still want to have that frequency but supply active power at a lower level or even at a higher level, you would then need to change the set points, and you would have a line that goes. So what you would do is you would then have a new value of no load frequency at which you would set your governor. All right. So what that means is, if, for example, imagine that your governor is running without being connected to any load. It is isolated. It has been disconnected from everything. It is just the prime mover rotating the alternator, and you're measuring the frequency that is coming out of the terminal points. At no load, at zero here, when you're supplying no load in those conditions, you could then set the governor to adjust the speed that it is outputting, right? So at zero, instead of running at, say, 1400 hertz, it would be able to run, say, 1400 RPM. You could run it at 1300 or something like that. And by dropping it like that, you drop the entire line to a lower level such that you can supply your P1 at the frequency that you desire. This is what we call governor set point adjustment. Okay. Normally, when it is running, you would not touch the governor set points. These are predetermined. However, if you want to now adjust, you can do so. Okay. So the governor set points that you put will determine if the load changes momentarily. Very small load changes, they will change along this line. So the frequency will alter along this line. That is why if you stand next to a generator, for example, when it is first switched on and you have a load applied, you will hear the frequency of the sound dropping. It is an actual change because the governor is changing. It's doing its job of changing the position of the frequency to match the load that is being supplied. However, if you have now longer term load requirements, that's when you can change the actual governor set points. The same thing would apply to our supply of reactive power. So if you want to supply reactive power at a value of Q1, say with a terminal voltage that is predetermined there, you would then be able to change the values of the voltage regulator. So this is voltage regulator. You change the values of the voltage regulator so that now it has a different, same slope, but it has a different starting point. So you would then have the same slope, but starting at a different point. Okay. So those are the characteristics of the governor and the voltage regulator. So once again, governor is prime mover speed and voltage regulator is field current regulation. Remember, with field current, we had a resistor, a variable resistor that was changing the value of field current, which in turn changed the value of induced internal voltage, which in turn affects the terminal voltage, which is what we are looking at in terms of these characteristics, right? So we go back to what we have said before. The voltage and the reactive power are controlled by the voltage regulator in terms of excitation. Active power and frequency are controlled by the governor in terms of the motion of the prime mover. So let's move to do an example. So here we are not looking at parallel operation, we're just looking at single operation and the changes that will occur to frequency and terminal voltage when we change the load in a generator. So this is quantifying what we've just talked about, the linear characteristics of generators in terms of active power and reactive power. So you have a generator with a no load frequency of 61 Hertz. That is the set point that you have set for this particular instance. The slope is given by 1 megawatt per Hertz. So for every megawatt increase, there's a 1 Hertz drop in frequency, right? As per the characteristic that we had. Load 1 consumes that power at that power factor, and load 2 consumes a real power of that at a power factor of 0.707. Before the switch is closed, what is the frequency? After the load is connected, what is the frequency? And what can we do to restore the system frequency to a desired value? Right, so let's look at that. So first of all, before the switch is closed, what is the operating frequency? So we have a number of things that can assist us in knowing that. So you know that power is equal to SP into FNL minus F system, right? So if we rearrange that, we will get F of the system is equals to FNL minus power over SP. So then we have 61 minus the power initially. So the power initially is 800. Sorry, it's 1000, not 800, 1000 over 1 megawatt per Hertz, right? So this is equal to 61 minus 1. It's actually equal to 60 Hertz. Okay, so that's the initial. After load 2 is connected, you then have the system frequency is equal to the same thing. We've not changed the set points, but the power has changed. Yeah, instead of 1000, we have 1000 plus 800. Okay, so it is this 1000, and then you have the real power of 800. So the two of them would be 61 minus 1800. So 1000 plus 800, 1 megawatt. The reason for the change is this is in kilowatts and this is in megawatts, right? So you can actually subtract them. So minus 1.8, it gives us 59.2 Hertz. Okay, that's after connecting load 2. So essentially what we've said is you had your initial load over here, but at a certain, when we connected P1, it traveled backwards and the frequency, we increased. So the initial one is at this point, and when you add, it now moves down to that point. Say this is P2, right? So there's a drop in frequency from here to here, right? That's the frequency drop that we've talked about. So from 60 hertz, it has dropped to 59.2 hertz, because for every megawatt increase, it drops by 1 hertz. So what would we need to do? Yeah, here what we are talking about is what we had discussed on this point. We want to run this generator at this set point, okay? So if we look at it diagrammatically, you have your set points looking like that. So you had your P1, which is 1000 here. Then you had P2, which is 1800 at that frequency. Frequency 1, this is frequency 2. So frequency 1 is 60, frequency 2 is 59.2. Okay, this is at no load, this is 0. So what do you need to do in order to get the machine to operate or to supply 1800 kilowatts, but at a frequency of 60? So you need to change your set point such that the P itself is at this point, right? Because you want to operate at 60 hertz. You want to bring it back to 60 hertz that we had in the previous example. So what we then do is what we talked about, the set points. So you will change the governor set points from this to this. So this is set point number 2, right? This is done by changing the governor, right? So for short term, you know, when you have a load suddenly increased, yeah, it would travel along the machine itself, right? Along the characteristic itself. It would not shift in between. For longer term situations where you know that is the load you're going to supply, you would then add or change the set point to match the situation that you would like to have. So that's the basic characteristics of machines: voltage, reactive power done by the regulator, active power and frequency done by the governor.